Greetings and a good time of day to you. A number of different power supply units were produced for ZX Spectrum computers over the years. Here's a summary of the main types. The two in the top left were made for the original rubber-keyed Spectrum. The leftmost one is marked Type UK700. This reflects its designed maximum output current capability of 700 mA. It's essentially the same as a ZX81 power supply, but with the correct type of output connector for use with a Spectrum. 16 and 48K Spectrums normally draw 500 to 600 mA, and so this supply is adequate. However, the total current draw could easily exceed 700 mA if peripherals are connected, and this could lead to the power supply overheating and failing. So take care if you've got one of these. Use of a very basic add-on, such as a joystick interface, shouldn't cause a problem. Sadly, the label on the supply can't always be trusted, as I'll demonstrate later. The unit next to it is marked UK1400 and is designed to supply up to 1.4 amps. It should be capable of powering all Spectrum add-ons that don't have their own separate supply. In the top right is a variation of the model to its left. It contains the same power supply, but the case was redesigned for the Spectrum Plus. All three supplies in the top row can be used to power the original rubber-keyed Spectrum or the Spectrum Plus. They should not be used with any of the 128K Spectrums. The bottom left power supply was produced for the first 128K Spectrum, the one with the metal heatsink attached to its side. It looks very similar to the supply for the Spectrum Plus, but with the addition of moulded serrations on one corner. It can supply up to 1.85 amps of current, and it's appropriate to use it to power the earlier models of Spectrum 2. It should not be used with any of the later Spectrums that have a built-in cassette mechanism. The final, grey power supply was produced for the first Spectrum Plus 2 and can provide up to 2.1 amps. It can be used to power any Spectrum that its output connector will plug into. All of these supplies are basic unregulated designs and operate in the same way. The only important difference is their power rating, i.e. how much current each type can supply. The later Black Plus 2 and Plus 3 Spectrums use supplies like these. They incorporate regulators and supply several different voltages to the Spectrum via a DIN plug. Both have the same type of connector, but the Plus 2 supply should only be used to power a Plus 2, whereas it's safe to use the Plus 3 supply with either. A Plus 3 will initially work with a Plus 2 supply plugged into it, but the supply will be overloaded and will likely fail after a while. Take care if you test one of these by using probes to check the voltages at the output plug. If you accidentally short any of the pins to each other or to the metal surround, internal fuses could blow or the regulator circuit be damaged. Fortunately, repair isn't usually too difficult. I won't say anything more about these supplies in this video. Here is what's inside a UK1400 supply. None of the Spectrum power supplies harbour dangerous voltages inside once unplugged from the mains. This might not be true if someone has fitted a different circuit inside the Sinclair case, so pay attention should you decide to open one. In some supplies, the transformer is mounted on a horizontal circuit board that fits over plastic pillars protruding from the base of the case. In others, a smaller circuit board is attached vertically to one side of the transformer. All of the supplies, apart from the later ones for the Black Plus 2 and Plus 3, and which I won't mention again, use the same circuit. Here is a diagram of it. It's about as simple as a mains power supply can be. It's designed to output approximately 9 volts DC. Being unregulated, this voltage varies depending on the current demanded. With no load attached, these supplies usually produce 13 to 14 volts. This decreases by several volts when a few hundred milliamps are drawn. The Spectrum is designed to operate with a supply of between 7.5 and 12 volts. This allows for considerable variation in the specifications of individual supplies and means the same supplies can be used with mains voltages between 220 and 240 volts, and probably even a little outside this range. Mains electricity is connected to the transformer's primary via a thermal fuse. This is an important safety feature and it should not be bypassed. If the fuse has failed, it should be replaced with one designed to disconnect at 104 degrees centigrade. That was the rating of the original fuse I found in the few cases where it had failed. When soldering the replacement in place, Remember, it's designed to fail if it gets too hot, so complete the job as quickly as possible. In some supplies, the thermal fuse is mounted on the circuit board underneath the transformer and inside an insulating sleeve. In other cases, it's underneath the plastic cover on the side of the transformer the mains connects to. It is covered with thermally conductive grease. A quick test of the likely health of the transformer's primary winding and the thermal fuse can be made by measuring the DC resistance between the mains input connectors. This can be done at the circuit board or the mains plug. 150 to 200 ohms is usual. An open circuit reading suggests the thermal fuse or the winding has failed. The transformer's secondary connects to a bridge rectifier consisting of 4 individual diodes. 1 or sometimes 2 electrolytic capacitors are placed across the output to reduce the ripple voltage. A total capacitance of 4,400 or 4,700 microfarads is common, but the precise value isn't at all critical. UK700 supplies, quite reasonably, usually employ a single 1000 microfarad capacitor. The supply connects to the Spectrum via a 2.1mm barrel connector. Unusually, the center terminal is the negative one. It's important to remember this if you want to use an alternative power supply. Many types are suitable, but usually the center terminal of their output connector is the positive one. This is likely to damage a Spectrum, and so the supply's connector should be replaced or rewired or an adapter used. The plastic strain relief around the output cable where it exits the case is not well designed. It's too stiff, and so it's common to find it broken or the cable damaged at this point. If you're lucky, you might be able to find a suitable replacement cable with a moulded-on strain relief from some other piece of equipment. An effective, though not quite so authentic replacement can be made from layers of heat-shrink tubing. Glue is added to the internal end to bond the sleeve to the cable, but don't get any on the external section, otherwise it'll become inflexible. I found this arrangement can withstand a very considerable pulling force before it breaks. A hazard could arise should the strain relief give way and one of the conductors break, followed by a misguided individual pushing the cable back into the power supply. It's unlikely, but possible the broken wire end could make its way to the other end of the case and contact the mains voltage. I think this is a safe design, but it might not comply with modern regulations. There is a 7805 voltage regulator inside 16 and 48K ZX Spectrums. It generates the 5-volt supply used by all of the logic circuitry. It also gets very hot, and this isn't good for the long-term reliability of the computer. The higher the voltage fed to the Spectrum by its power supply, the hotter this regulator becomes. Typically, it has to waste a bit more than half a watt extra for each 1 volt increase at its input. Under most circumstances, Spectrum power supplies output 2 or 3 volts more than is necessary. It would be nice to prevent this. A very simple way to improve the situation is to wire a diode in series with the power supply output. This drops about 1 volt when it passes the current drawn by a Spectrum. Adding 2 diodes in series would help further in many situations, though I usually stick to 1 to make sure the output voltage can't become too low when various peripherals are attached to the Spectrum. Here I am inserting an ordinary silicon diode rated for a continuous current of 3 amps in the negative power supply lead. This is the one that connects to the centre of the output plug and is normally the one with the stripe on it, but it's best to check. It doesn't matter which lead the diode is inserted into, but, of course, it must be fitted the correct way around. The diode will become warm in use because it dissipates power that would otherwise heat up the Spectrum. Leaving the full length of the diode's leads helps it to radiate this power and prevents it from becoming too hot. They can be bent over to make it easier to fit it inside the power supply case. The whole assembly is covered with heat shrink tubing to electrically insulate it. While dismantling several Spectrum power supplies, this is what I found inside two of them, shown here in front of the top part of the case each was in. The one on the right has a smaller transformer and a 1000 microfarad capacitor, and so I suspect it's the one rated to supply a maximum of 700 mA, contrary to what is marked on the outside of the cases. Testing should quickly reveal which is which. This equipment is set up to form a simple circuit that I'll use to test several power supplies. Various power resistors can be connected to provide a load. The meter on the left displays the voltage at the supply's output plug, and the other the current through the load. An oscilloscope is used to display the ripple voltage. The signal shown by the oscilloscope when no load is connected to the supply is due to interference from the mains that is coupled to various leads. It can be ignored. Once a load is connected, the ripple is clearly visible. It should have a frequency of twice that of the main supply, making it 100 Hz in this case. If it's equal to the mains frequency, then most likely one or more of the rectifier diodes is faulty. Here are the results of the tests on 4 ZX Spectrum power supplies. 3 of them had had a diode inserted in series with their output, and their reservoir capacitors had been replaced with brand new ones. The line labelled UK1400 Original shows the results for an unmodified supply. The voltage reducing effect of the diode is clear to see. The green UK700 line is for the supply I found inside a case labelled UK1400. Its true identity as a 700 mA supply is revealed by its voltage falling away more rapidly as it's asked to supply more current, even though it started off with a higher unloaded output voltage. During the tests I drew slightly more current from each supply than it was designed to deliver, but only did so for a short time to avoid damage. This graph shows how the peak-to-peak ripple voltage of the same supplies varied with output current. The grey line shows the predicted ripple for a supply with a 4700 microfarad reservoir capacitor, which is what it was in all of the supplies apart from the UK700 one. I had replaced its 1000 microfarad capacitor with the 2200 microfarad one. Increased capacitance reduces ripple, but increases the peak current that must be handled by the rectifier diodes and the transformer, so it mustn't be increased too much. The ripple has negligible effect on the operation of a spectrum, and so there's no need to make special efforts to reduce it. The calculation for the predicted ripple assumes the load is a constant current one, which it wasn't, being a simple resistor. This probably accounts for much of the difference between the prediction and the measured behaviour. It's normal for there to be quite a bit of variation between individual spectrum power supplies, but should the results of tests like these be very different, the supply is probably faulty. I haven't presented any test results for the higher capacity supplies for the first 2 generations of 128K spectrums, but they should be similar, other than the output voltage remaining within the range suitable to power a spectrum, at least until the current reaches the maximum the supply is designed to be able to provide.